Welcome to the G Lab and zero G. Although not quite zero G, there's actually no place in the universe you can go where there is zero G. There's always some gravitational pull acting on you from somewhere, even if it's from trillions of miles away. There's a little bit of gravity everywhere. So we'd call it microgravity is probably the better term for it. It's time for Spaceballs. We're going to take a look at what happens when you put some spheres out in space and how they would move. So let's take a look. By the way, if you haven't seen Spaceballs, the movie, pretty darn funny. All right, so here we go. We're going to put a couple of baseballs out in space, and what would happen to these? Well, make a prediction. All right, and these two Spaceballs here are going to move together. They'll start out kind of slow because they're far apart, and as they get closer and closer together, they will accelerate. And eventually their centers of mass will be trying to get as close as possible to each other. Gravity pulls things together, and so those balls will eventually come together. Now, if those two baseballs start out closer together in space, they will move a lot faster because they are closer. And gravity is caused by mass and also by distance, and the distance apart makes a big difference. They will come together quite a bit faster if they're closer together. All right, let's take a couple different spheres. We've got a golf ball and a bowling ball. What would happen with these guys? Well, they would obviously come together just like that. And as you can see, the golf ball moved a tremendous amount faster and farther than the bowling ball. Did the bowling ball move at all? It actually did. Watch carefully. The bowling ball does move a little bit towards the golf ball. And that's because the golf ball also has a bit of gravitational pull. It has mass. So it's pulling on the bowling ball, and they're actually pulling on each other with the same amount of force. And if you think about this, if you were to put a very light person in a rolling chair and you push them, they're going to move pretty fast. If you put a heavier person in a rolling chair and push them with the same amount of force, they're not going to move as far or as fast. And that's exactly what's happening here. There's the same amount of pull going on between these two objects, but the larger one is just not going to move very far. That actually looks a little bit familiar, kind of like when I dropped the duck on the Earth. So which one of these represents the duck and which one represents the Earth? It's a pretty good analogy. Yep, the bowling ball represents the Earth, and the golf ball represents the duck. The Earth actually does move slightly toward the duck when you drop it. Now, of course, the difference between the duck and the Earth is enormous compared to the difference between a bowling ball and a golf ball, but the analogy works pretty well. All right, it's time to learn how to draw vectors. That's right, vectors.
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
And just like vector, vectors are this. They are arrows that show both direction and magnitude. Magnitude simply means the amount. So the magnitude, for instance, of an earthquake is how much it shakes, essentially. The magnitude of something is how much. So arrows can show direction, obviously, by which way they're pointing, and they can show magnitude by how long the arrow is. A shorter arrow shows a smaller amount, and a longer arrow shows a greater amount. So let's draw some vectors on this system right here. We've got a golf ball and a bowling ball, so what's going to happen? Well, we need to start with the center of mass of each of these, because that is where the direction is going to go from and to. So it's from one center of mass pulling toward the other center of mass. Remember, the center of mass doesn't actually cause any kind of gravity. It's not something special about that point. That's just the average of all of the mass in this object. And so what's going to happen? We can show the direction that the golf ball is going to move with an arrow in that direction, and the magnitude of how fast it's going to move with the length of the arrow. So we just choose a nice long arrow like this for the golf ball. And how much is the bowling ball going to move? Just a tiny, tiny amount, but in the direction toward the center of mass of the golf ball. All right, let's try this, and there's obviously what's going to happen. So let's try this with another system here. We've got a bowling ball and two baseballs equidistant on each side. So center of mass of each of those. This baseball here is being pulled toward the bowling balls, toward the center of mass here, and also being pulled by the baseball way over here on the right. Not as much because it's a smaller, less massive object, and it's also a lot further away, but it's being pulled in this direction. The baseball on the right obviously is being pulled in the other direction, so they're going to go toward the center like so. And what about the bowling ball? Is it being pulled? It is. It's being pulled in two directions toward each baseball. And if the bowling ball was a squishier, more moldable object, it would probably bulge or even tear in half, but it's not. It's pretty solid, so it would essentially just stand still. The idea here is that these two arrows cancel each other out, and the net movement is going to be none, and those Spaceballs will come together. All right, how about this one here? Make a prediction. All right, hopefully you made a prediction, and here is what's going to happen. What? The beach ball is so huge compared to the bowling ball. It is bigger, but big isn't necessarily what we're talking about here. Is mass the same thing as big? No, the beach ball has very, very little mass, but it is big. But mass is what matters. So the bowling ball has far more gravitational pull than the beach ball because it is so massive. It has so much more mass compared to the beach ball. The beach ball is mostly filled with gas. All right, here we are with 3 different baseballs. More fun with vectors. It's time to actually combine some vectors. So if we look at the baseball on the right here, we see that it is being pulled by 2 different baseballs. The one up here is pulling the baseball this direction, and so we're going to draw a dashed line here, a preliminary vector, and the other baseball here is pulling it this direction. So it's actually being pulled in 2 different directions. And so we're going to draw these dashed lines as preliminary vectors. We'll combine them a little bit later on. This baseball here is being pulled the same amount, and it will move at the same speed toward the baseball on the right because they are the same size and they're going to pull toward each other. And what about this one down here? How is it going to pull on this baseball? Well, it's going to have more gravitational pull because it is closer. Same mass, but it's much closer, so it's going to have a longer arrow showing the magnitude being more. And again, same thing with the baseball down here. When I say down here, we're in space, so there is no down really. It's just on the screen down here. And again, it's being pulled toward the other baseball here with more force because it's closer. Okay, so what do we do here? We've got these baseballs that are going to move, but they can't move like this. Like, it's not going to move along that line and then go back and move along that line. It's not going to split in half and move toward both of them. It's going to move in one direction, but where? So here's what we have to do. We have to combine vectors. And how do you do that? Well, let's look at it and think of it like this. Imagine that you're under arrest by this Roman guard here, and he says, take 4 steps east, take 3 steps north. Thanks. So what are you going to do? Well, you're going to take 4 steps east and then 3 steps north, right? Wait a second. That doesn't look right. That's not how it would work. But yet that's how we've drawn our vectors. We've drawn them from the center of mass in 2 directions, but it doesn't really show us where you're going to end up or where you're going to go. If you were actually going to follow this guy's directions, you would take 4 steps east and then 3 steps north from there, and you would end up here. So how do we end up here? What we can do is we can draw the vectors first, and then we take this one and move it to the end of the other vector. So we stack them together, one after the other, and where do you end up? You now can draw a line to where you end up, which is right here. It's like taking 5 steps kind of toward the northeast. So let's apply that then to our baseballs here. How do we figure out which direction this ball here is going to move? Well, we need to stack the arrows. So we move that arrow, move that vector, and notice that it was pointing at this baseball over here, but when we move it, it's now pointing off into nowhere. It's pointing in the same direction. It has the same magnitude, the same size. We've just moved it and stacked it. And where's this ball going to move towards? Right there at the end of these 2 vectors. Okay, so it's going to move in this direction. Here's our final vector. These are kind of a rough draft of where it's going to go, but this is our final vector. Same thing with this baseball down here. We can move that arrow, stack them, and where's that ball going to move? Right there. Now, how do you know which arrow to move? It doesn't even matter. You can move either arrow. Check this out. If you move this arrow here to the end, look where you end up, in the exact same spot. Okay, and again, you're just sliding it along. You're keeping it the same. It's almost like a parallelogram, really. You can kind of, either arrow that you move, you're going to make, you're going to end up in the same spot. So with this one over here, move the arrow and stack them, and there you go. Now I always take a look and go, okay, does this make sense? Is this baseball here going to move this direction? Well, yeah, it makes sense because this one is closer, so it has more gravitational pull, so it's going to move not directly between these two. It's going to pull more toward this one. This one over here is being pulled equally by both of these baseballs here, and so it's going to move directly toward where they are in the center. And eventually, as these balls move, their vectors will change as they move. Right? When these two baseballs come together, now they're not moving off in different directions. They're actually being pulled toward the single baseball over here. So the vectors are constantly changing as conditions change. So let's try this with a more complicated situation here as practice. We've got a golf ball, baseball, and a bowling ball, 3 very different masses. And the distances are different, so it's a little trickier here. What I usually do is I start off with the smallest, or I should say the least mass object, the object with the least mass. And the idea there is I want to draw my longest vector first to make sure that I've got enough room for all the vectors. So where would the longest vector be? Would it be toward the baseball or toward the bowling ball? Well, the baseball is closer, but the bowling ball is probably 10 times as heavy. It's got way more mass, so it's going to pull that golf ball quite a bit more. So let's go ahead and draw our first arrow. We'll draw a nice long one. I usually try and draw a good at least halfway, or maybe 2/3 of the way. You could actually calculate how long to draw these if you knew the mass of all these different objects and the distances, but we're going to keep it simple. And so this golf ball is being pulled toward the bowling ball in quite a bit, and the golf ball is being pulled toward the baseball not as much because it has less mass. So the second arrow here, our second preliminary arrow, is going to go toward the center of mass of the baseball, but not as far because it has much less mass. All right, let's try the bowling ball. And the bowling ball here is going to be pulled toward the golf ball a tiny, tiny amount because it's a long ways away, and also it has very little mass. So how long is our arrow? Just a cute little arrow. Just a cute little arrow right there. It's tiny. Tiny little arrow. What about towards the baseball? More or less? What do you think? Bigger arrow, smaller arrow? It's going to be a bigger arrow because this baseball is much closer and has more mass. So it's going to have a larger arrow going that way, about like that, maybe even a little longer. And finally, the baseball is being obviously pulled far more towards the bowling ball. Is it going to be as much of an arrow as this one here, this long one from the golf ball? Probably not as long, although it is a little bit closer. It has a little more mass, so if you're putting this guy in a rolly chair compared to the golf ball, it's not going to roll as fast. It's not going to move quite as fast. So as we draw those arrows there, it's not quite as long, and then toward the golf ball, of course, it's really quite short because not a whole lot of pull from the golf ball. Okay, let's combine some arrows, combine these vectors into a final vector for each of these. So for the golf ball, we're going to slide one arrow there. Notice, is this arrow still pointing toward the baseball? No, it's the same direction, it's the same length. You just picked up that arrow and moved it over here. So you just draw another arrow over here, and that's the point that your golf ball will begin to move toward. And does that make sense? Look at it and go, yeah, it's going to move fast, therefore it's a long arrow. And it's going to move more toward the bowling ball than it is toward the baseball, which makes sense because it's much more mass. The bowling ball, let's go ahead and stack those arrows. Cute little guys. And it's going to move something like that. Good. Again, not very much. And in about that direction. Looks good. And finally, we'll move this final arrow here, and the final vector for the baseball is right there. And it's going to move about like that. And this one makes sense again. Look at the lengths of the arrows compared to each other. You've got a long one for the small object, medium one, and a very short one for the more massive object. And so as these guys move, they're going to move something like this, and and their centers of mass will come as close together as they possibly can because they are being pulled toward there. Because there is no down, there is only together. That's right, objects will always move together, and that's how you do it. Vectors, spaceballs, gravity. Thanks for joining us.